Hello everyone, I hope you all are doing well. This side Priya Bhatia, and I'm really excited to announce that now I think we are in a situation where we will start our very first algorithm of boosting part. See, till so far I have covered up the core idea behind boosting. We have seen that what's the inference behind these boosting algorithms. Now I think it's the right time that we should deep dive into all of the three algorithms that we have. So in the very first portion of this module, you will observe that I will be talking about adaptive boosting algorithm. It's also very widely famous by the name of Adaboost. So let's try to talk about the maths behind Adaboost first. Then whatever things I will talk about theoretically in the upcoming sessions, you will see that I will be trying to write a code for the same, because then only you will be able to correlate each and everything in a lot more detail. And at the very end, I will showcase you that how basically via sklearn, you will be able to implement this specific algorithm and what are the hyperparameters that we have to take care of whenever you are applying this algorithm in any of the industry level project. So without wasting any time, let's get started. So now let's deep dive into this algorithm. As you can see from the image itself, I think this would be pretty much clear to everyone that what we are doing here is specifically, we are trying to somehow, this is our training set that we have, right? Consider that this is our training set that we have. So we are passing the data points that we have to the algorithm. For example, here we are working with, let's say DT1, decision tree 1. What will happen is that this decision tree will try to specify some decision boundaries. So whatever you can see with this red mark is, you can consider as a decision boundary that we have. Now what will happen is, you can see in this decision boundary, there is one specific point which is misclassified. So that specific point we will give as an input parameter to the next important model that we will train. Now, once this training will happen, what will happen is that you will be able to observe this decision boundary is now correctly classified, but above all of them are misclassified. So what you're observing here, that at every iteration, at every stage, we are passing, or our model is passing all the misclassified, you can say, data points. I think this is what I have talked about in my previous core idea intuition wala video as well, where I have shown you that how basically with the help of one layman example, that if let's say teacher is giving 5 questions to the students, and what is happening is, let's say 2 questions a student has done it correct and 3 are incorrect, so that 3 questions were passing to the next student, and that is how the complete flow is going on. Same thing is happening here. So what we are saying, that we are passing the training set as a whole in the very first part, in the very first iteration. There is a decision tree which is working internally. Now what is happening is, somehow obviously there will be some misclassifications, and whatever be the misclassified data points that we are getting, we are passing that to the next iteration, and this step will be keep on repeating. This is something which is going on, right? So that is why, if you will be able to see, again same thing is happening. There will be a misclassified points which will go again. If you can see, there is another thing, same misclassified points will go to the second iteration, third iteration, decision tree will run again, new iteration will come up, and finally we will be able to get the, you can say, final model with us, which is, you can say, is a strong learner, right? So this strong learner is nothing but, you can say, is a combination of various weak learners available in the data. Can I say this? So it is nothing but it's a combination of various weak learners which are working internally in a given set of data points that we have. Make sense? So this is something which is really, really important to understand. I hope it makes sense to everyone. And that is why we are calling it as a sequential learning. So this boosting technique is a core component, or a core idea is the sequential learning. Why we are calling it as a sequential learning? The only reason is that until or unless I won't be able to get the result of my first model, or I will not able to evaluate that how many number of points are misclassified, I won't go to the next model, right? I won't pass the results to the next upcoming model that we have. So that is why it is called as a sequential learning. This model is basically doing nothing but sequential learning, combining all the weak learners, and will be able to give us a strong learner at the end of the day. That's the core idea, right? Now, let's see the maths behind that how basically this is working internally. And please try to listen the maths very, very carefully, right? Some people got confusion that, how is the things are happening. I will try to convey it in a very small, simpler steps, so that if in future you will refer the book also or website also, you will be able to clearly understand that how is this working. It might be a long video, so please be patient and try to watch it till the very end, okay? And just try to watch in a continuous manner so that you will get that flow, that how the things are working internally, okay? Now, let's say we will be having, I'm taking one sample data and I'm just taking only, let's say 5 data points available in my data. Okay? So let's assume I have written the 2 features. Let's assume that we will be having 2 features in a given data, F1 and F2. And here I will be just showcasing you for the demonstration purpose. Let's say we will be having the data points 1, 2, 2, 3, 3, 7, right? 2, 9, and let's say 9, 8. Some random points I have mentioned. It's very random. So we have 2 features. Both of them are having a numeric data available with us. In total, number of data points that we have is 5. Okay. So we have 5 data points available with us. Now what will happen is, it's a supervised learning. So your value of y is also given to us, which is the actual label of a particular feature value or record value that you have. And let's say that labels are 1, 0, 1, 0, and 0. Now, let's try to understand that how basically the very first decision tree will work and what things it will be able to convey to us. Before that, whenever we are talking about the weights part, if you remember in our previous discussion when we will be talking about the difference between bagging versus boosting versus checking, we have seen that somehow the weights plays a very important role in boosting algorithm. And I told you also that in this algorithm specifically, whenever our model will do somehow misclassification of data points, we will try, or our model internally try to assign the higher weightage to that specific, you can say, misclassified points as comparable to the data points which are correctly classified. So the weightage of the misclassified data points will be higher as compared to the correctly classified data points. Now the question will be that how is that be done, right? What is the core idea behind that? How mathematically my model will be automatically assign the higher weightage to the misclassified data points and a lower weightage to the classified data points. So there must be initial weight initialization, right? What was that? So always remember, in this model, the initial weight initialization, which our model will do internally, will be 1 divided by the number of records that we have. So in this case, we will be having 5 records. So it will be 1 divided by 5, which is equals to 0.2. So initially, every particular record will have the same weightage because we are just starting our algorithm. So every particular record will have a weightage of 0.2, 0.2, 0.2, 0.2. Same weightage will be there. Now what will happen? You will try to train your first decision tree, DT1. Okay, DT1. You will try to pass all the training sets available, which is 5 in our case. And we will train our DT1 model because now we have 2 input features and we have the target value also available with us. And let's suppose you have trained your model and your trained model is ready and you will be able to get the predictions out of that model, right? Which is y cap. So one thing which you have to remember in this Adaboost algorithm, this decision tree algorithm which we are talking about is called as decision stumps. And one interesting thing about this algorithm is that the maximum depth which this decision tree will entertain will be equals to 1. Now you can ask me the question that Priya, why is that so? Because here we are trying to not curate a perfect model altogether. We are trying to curate a weak learner having a maximum depth as 1. And on the basis of that, whatever be the tree we will be able to get, for example, let's say we will be able to get, let's say, the value of F1 You all know that somehow it will compare the Gini or the entropy value, will curate some decision boundaries, and let's say F2 less than 10. I'm just giving you one random sample, but this is how basically the tree will be curated. And at the end, we will be having a leaf node, which either contains the value as 0 or will contain the value as 1. So everything, whatever I'm telling you here, we will be able to see all these things in the practical demonstration in the upcoming session. But this is how basically the decision tree will be curated as per the 2 sets of data points that we have, and the maximum depth you will be able to see for that decision tree will be 1. In Adaboost, we're calling that as a decision stumps. Now let's say you curated that. Your model M1 is ready, DT1 model is ready, and with the help of that DT1 model, you're trying to make the predictions now. And let's suppose you're getting a prediction as 1, then you're getting the prediction as, let's say as 1, then here it is 0, let's say, here it is 0, and here it is 0. I have just done the calculation before, that's why I'm just referring those particular points only, so that it will not take much time to me to do the calculation in the recorded part of the video. That's the whole objective. Now here, if you will be able to see, this is the prediction given by model M1, which is nothing but DT1. In this case, you will be able to observe there are 2 misclassifications which my model has done. There are 2 misclassifications which my model has done, right? In second record, where the actual data is 3, but the labeling is 0, but my prediction is saying the outcome should be 1. And in the record number 3, actually it is 1, but my model is saying that the output should be 0. Both are misclassified data points that we have. Or in other words, you can say it's an error. So if I will ask you what is the total error of our model, so in Adaboost, error is the summation of the weights values which are misclassified. So it is 0.2 plus 0.2. So if you will just add these 2 numbers, this is the total error in your DT1 model which you are getting. Make sense? Now the question is, what we have to do in the next iteration is, when we pass the next iteration, we have to update these weights. We have to update these weights in such a way that whatever be the points which are misclassified, they will be having a higher weight value, and whatever be the points which are correctly classified, they will be assigned a lower weight value, so that it will be able to give an indication to the model that you have to majorly focus on these 2 points which are misclassified. So now how is that be done? There is one parameter which we call as alpha, which plays a very, very important role in terms of doing a weight initialization or in terms of updating the weights. Alpha is something which you can say is the models say, right? Now, if let's say I'm saying that my model is having an error of 0%. In that case, there is one model, let's say I'm having a model M1, which is having an error of 0%. Then we have a model of error M2, which is, let's say, is having an error of 50%. And then we, let's say, have an error in model M3. We have 3 models with us, and let's say the error is 100%. So the alpha value is inversely proportional to somehow error. For the model M1, which is having a lower error, it means that the value of alpha is very, very high, means that model says very, very high. For the model which is having a highest error, the value of alpha will be very, very low, means it is in a negative quantity, right? And when the error is 50%, this is something which is a very, I would say, dangerous situation for my model. Because somehow when I'm saying the error is 100%, if I will do 1 minus this specific term of error, I will be able to get the alpha. But it's when I'm saying 50%, it means 50% of the time model is giving me the correct result. 50% of the time my model is giving the wrong result. It's a very impure sample or result that we are getting, right? At least 0 and 100 is a good idea, because somehow we will be able to get an idea of alpha with the help of the indication of error part. So either the models say will be very, very high, or it will be very, very low. Depending upon that, there is one plot which usually being designed between the, you can say, value of alpha and the value of error. So as the error is very, very low, let's suppose this is the situation where the error is very, very low, alpha is very good. And the situation where the error is very, very high, for example, let's say we are starting with a point from 0 to, let's suppose, 1. This is the maximum point. Then the value of alpha we are saying is negative, because it's something where my model says very, very less. But when the value is, or the error is reaching towards 0.5, in that case, we are not considering that model altogether. It's a alpha value is also 0. So this kind of graph you will be able to see, we will be able to plot here. Somehow this kind of a graph going like this curve and then this curve, something like this. And this is a curve in maths is defined by an equation which is equals to 1/2 logarithmic of 1 minus error divided by error. So we will use this equation to update the weights. Okay? So what is alpha? I hope this equation is clear. 1/2 logarithmic of 1 minus error upon error. This is the equation of this specific curve which I have just now plotted here. I have just tried to give you the intuition behind this curve. Now, at every point of time, wherever there is a misclassification, what you will be able to observe is that the formula to evaluate a new weight, or you can say updated weight will be somehow equals to what is the current weight multiplied with e to the power alpha 1, because alpha 1 is the, you can say, value for DT1 model. When we move to the next model, our value of alpha 2 will get changed, then alpha 3. So as many number of models you're using, as many number of alpha values you will be able to get. And at any point of time, whenever your model is correctly classified, what you are doing is, you are trying to decrease the value from the original weight. So your updated weight will be equals to what is the current weight multiply with e to the power, let me go up so that you will be able to see what I'm writing in the screen, e to the power negative of alpha 1. If I just have to showcase you the plot of this specific value, let me just showcase you so that things will be in a better picture to everyone. So I'm just using this graphing calculator. If I'll say y is equals to e to the power x, alpha I cannot plot, but you can see, right? As we are approaching, the value keeps on increasing. So if you will multiply this with any of the number, you will be able to see that your values will keep on increasing. I hope you can see that. And this is what I want. What I want is that for the model which is having a misclassification, the value should be in a negative point, in a positive note, it should be higher, right? So that my model will be able to get an idea that, okay, this is where misclassification is happening and this is what I have to focus more in the next iteration. Wherever there is a correctly classification happening, so we are doing e to the power of minus x. So can you see our curve is going towards negative direction? Can you see this? I hope you can clearly see this. Your value of y is going towards negative side of x, right? 0, minus 20, minus 40, minus 60. It means that whatever number you will multiply with that number, it will become lesser value. So this is how basically the weight update will happen. Now, in our case, our error in this example is 0.4. Just now we have evaluated because two misclassifications happened. Error is nothing but is the addition of the current weights that we have, which is the addition of 0.2 plus 0.2, which is 0.4. Now, what we will do is we will try to evaluate the value of alpha 1. So let's apply this formula of alpha 1, which is, you can say 1/2 natural log of 1 minus 0.2 divided by, so it will be 0.8 divided by 0.2. If you will just try to evaluate this equation, it is 0.2 or 0.4. Sorry, it is 0.4, right? So let's rectify this. It is 0.4 upon 0.4. Somehow we are getting 0.6 upon 0.4. So you will see that this value will come out to be 0.20. I have done the calculation prior. So this is the value which we are getting for the alpha 1. So now if you have to update the misclassified points weight, it will be 0.2 into e to the power 0.2, and for the correctly classified weights will be 0.2 into e to the power of minus 0.2, right? So if you will just try to solve this specific part, it will come out to be 0.24 in this case, and it will come out to be 0.16 in this specific case. So what I'm saying is, your new updated weight will be, wherever there is a correctly classification, it is 0.16. Wherever there is a misclassification, it is 0.24, right? It is 0.24. It is 0.16. And it is also 0.16. So this is the updated weight which we will be able to get at the end of the day, right? Now, what we will do is, in the next step, if you will do the addition of these weights, this is not coming out to be 1. So we have to normalize these updated weights. So how the normalization will be done? The value of 0.16 divided by the total sum that we are getting here. You can just do the addition of these weights. Let me do it. I have not done it prior. So let me do it just now. So 0.24 into 2 is, I think, 0.48 plus you can say 0.16 into 3. So if you will solve this, we are getting the correct answer as 0.96. So to normalize this value, what we have to do, 0.16 upon 0.96 into 100. So here you will be able to see the normalized value will come out to be 0.166, 0.25, 0.25, 0.166 and 0.166. Now if you will do the addition of these points, you will be able to get the accumulation of these results as 1. So this is the normalized weights you can say that we will be able to get for all of these 5 records that we have. Next task is to convert these specific values in a cumulative range. So what we will do is, we have normalized values available, extending that table itself. Now I'm trying to convert it into a cumulative range of the numbers for all the 5 data points that we have. So what we will be able to get is from 0 to 0.166, 0.166 to 0.416, 0.416 to 0.666, 0.666 to 0.832 and 0.832 to 1.0. So we have 5 records available, 1, 2, 3, 4 and 5. And in all of these 5 records, what we have done is we have just taken the range. So 0 to 0.166 is the first range. Then you can add this value 166 plus 0.25 and accordingly you can try to specify all the ranges from 0 to the 1 wala part. And that is what I have done from that normalized factor. Now what we will do? How basically we will be able to approach to the next iteration. So with respect to the DT1, it is clear, I hope. Till so far what we have done, I'm just giving you a brief recap before we will jump towards the next iteration. So if you remember, we have the train set available where we will be having the 5 data points. So what we have done till so far, we have passed this train set to the first decision stump, decision tree DT1, where the maximum depth is 1. Our model, when we apply this, will be able to give us a result of y cap. We have the value of y also. We will see how many of them are the misclassified points we will be able to get. With the help of that, we will be just doing by addition of weights, we will be able to get the result as the error. And how basically the weight initialization will be done in the DT1 part itself. The weight initialization is nothing but as we have seen, it is simply 1 upon the number of records that we have in the very first iteration, number of records, right? Now, once we will be able to get an idea of the error, we will try to see the value of alpha, which is 1 by 2 logarithmic of 1 minus error divided by error. Why is that so? Because of that curve which I have just now explained to you. Once we will be able to get that value of alpha, we will update the weights. Next task is to update the weights. Now, this weight update will happen differently for the classified points and misclassified points, because the ultimate task is to increase the value of the original weights for the misclassified points, so that we will try to give more importance to the misclassified points as comparable to classified points. So for all the misclassified points, we have seen that it will be nothing but whatever be the original weight we have multiplied with e to the power alpha 1. But for all the correctly classified points, the value will be equal to the weight into e to the power minus alpha 1. So in this way, we will be able to increase the weight of misclassified points and decrease the weight of correctly classified points. Once we will be able to get that, we will try to normalize that weights if the sum is not equal to 1. And then we will try to apply a range. So we will try to convert that into a specific ranges that we have. Once it is done, now how we will be able to approach to the second iteration, which is DT1 is ready now. We have to pass the maximum misclassified points as the train set to the new model. I hope this is what is our next task, right? So here what we want is, we now want to get the new training set. New means that is a part of that original data itself. But now in this train set, what I want is, I want misclassified points only. Misclassified points only. So that my model will be prepared for next DTT2 and it will focus more on the misclassified points. How it will be done? How we will be able to get in a training set maximum misclassified points? So for that, what we will do is, we will apply random numbers. We are saying that give me some random numbers in the range from 0 to 1. Now what will happen is, let's say we will be able to get some random values like 0.13, 0.43, 0.47, 0.74, 0.80. So what is happening is, this specific range belongs to class, I think 1, belongs to the number of record as 1. Just check it out. This range 0.43 belongs to the 3. This specific range of 0.47 belongs to the third record. 0.74 belongs to the fourth record, and 0.80 also belongs to the fourth record. Now, what is the intuition behind curating the random samples, taking the random samples from the record? So what I will do is, now I will just pick up the 1, 3 and 4 as a training set of mine. See, what is the intuition behind that? Whatever be the points which are misclassified points. For example, in my case, in my demonstration, point number 2 and point number 3, if you remember, these two are the misclassified points, right? Misclassified points. And for the points which are misclassified, what you will be able to observe? You will be able to observe in those specific instances, the range is bigger, right? The range is higher. Why? Because the value is somehow bigger, the weight is bigger. So what will happen is, for all the misclassified points, the range will be higher. So when you are taking the random samples, when you are taking a random data points, what will happen is, the probability of having misclassified range will be higher. Can I say this? Because whatever points we have belongs to the misclassified points, their range is very, very big. So when you are calling the random data points randomly, obviously the probability of falling into this bigger specific ranges is very, very high. So what will happen is, by default, definitely you will call many random samples. So by default, what you will be able to observe, that maximum data entries will belong to the 2 and 3, right? Maximum data entries will belong to the 2 and 3, which are the misclassified points that we have. And this is how same thing will happen again. So consider that, let's say here you can see 3 and 4 are coming up higher, but here though I have just taking it randomly, but when our model will take the random numbers, definitely the chances to fall into the second and third category is very, very high. What I'm trying to convey here is, maybe chances are very high that you will be able to get the result as 0.20 or 0.31. So in this case, it belongs to again class 2 and class 2. So what will happen is, your DT1 contains the high samples which belongs to class 2 and class 3, because those are the misclassified points that we have. Now same thing we will do there also. We will try to evaluate the DT2. Then with respect to DT2, what is the value of y cap? Then once we will be able to evaluate the value of y cap, we will check the error rate by adding all the misclassified points that we have. Then evaluating the value of alpha. Then updating the weights by using that formula of e to the power minus alpha 2 or minus alpha 2. E to the power minus alpha 2 for the, you can say, classified points, and e to the power alpha 2 with respect to the misclassified points. So same, whatever points we have discussed in iteration number 1, we have to repeat the same things to the iteration number 2. And that is how basically this boosting algorithm works. That's the main intuition behind that in every iteration, we are just trying to check the values of alpha 1, alpha 2, alpha 3, alpha 4, and so on, depending upon how many models we are applying. Evaluating the weights, updating those weights in a way that for all the misclassified points that we have a bigger weight value. And for the classified points that we have correctly classified points, I would say, we will be having a smaller weight value. And that is the core idea behind how this Adaboost algorithm works. And that's why it's called as adaptive boosting algorithm. The full form of Adaboost is adaptive. So my model is adapting as per the given data points and giving in the sequential part of the training, adaptive boosting algorithms. So this is the core idea behind this Adaboost. I'm just taking a pause here. Whatever points I have just now talked about with respect to how the training will happen, I hope it is pretty much clear to everyone. Still, if there is any confusion, you can just rewatch the video again. And then maybe in the upcoming session, we will try to start our new discussion where whatever things I have mentioned in this notepad editor, in this sheet which you are seeing here in the live session notes, I will try to do the implementation for the same so that things will be pretty much clear to everyone. So now I hope that you will be able to get the internal intuition behind Adaboost algorithm. In the upcoming video, we will be talking about the code implementation for the same. So whatever things we have covered up till so far, whatever steps you have explored till so far, you will observe that all of these steps we will be covering up in our upcoming video via doing the code part. So please make sure that before jumping towards the next particular video, you will just try to understand all the concepts, whatever I have covered up in this specific video. If there is any confusion, please try to rewatch the video again. Sometimes it might feel bit maths heavy, but believe me, it's very easy. If you will be able to document your learning, if you will be able to write each and every stuff and try to think over it, that whatever points I'm trying to convey, what is the inference behind that, and do refer the standard book side by side. As I always say that referring one standard book will be very helpful whenever you are learning something new, right? You can just try to read out the stuffs, whatever I have covered up in that specific book of hands-on with machine learning. I think that will give you a more better idea. With this, let's end today's video. I will see you all in the upcoming video where now we will deep dive into the code implementation for the same. Bye-bye everyone and see ya.